Hello there, welcome back to Learning with George. I had a request this week to do a tutorial on compound interest, which is what I've got for you today. Compound interest is something that is useful for anybody to know about because it can be really helpful when you're trying to plan for the future in terms of your finances, whether that's knowing how much money you're going to have after a certain amount of time if you have got a compound interest rate on a savings account, or knowing how long it'll take you to pay off a loan if you have a compound interest on that. So here's a little bit more about it. Okay, so compound interest. What is it? Why is it important to know about? And how can we use it to calculate future targets? So we'll start by defining interest. This is money paid for the service of borrowing money. So in the example of a bank, people give money to the bank, they deposit money into the bank. The bank uses it for giving other people loans and other services. And then at some point, the bank's going to give back the money that was deposited plus a fee for borrowing it. And this fee is called interest. Now, there are different types of interest. So firstly, the simple interest, which is interest calculated according to the initial amount borrowed, regardless of how long the money is borrowed for. So essentially, there'll be money deposited. In this example, we've got £500. There'll be a simple interest rate, let's say 10%, and then the total amount that you're going to be able to withdraw is going to be £550, which is the initial deposit plus the percentage of that deposit that has already been agreed. And this is not dependent on time. This is sort of whatever point you're going to give back that deposit plus the interest. Now, compound interest is slightly different. This is interest calculated according to the initial amount borrowed plus the amount of interest accumulated over time. So let's illustrate that by saying, so we've got the initial deposit, which is also known as a principal. That goes into the bank. Let's say you've got an annual interest rate. Then at the end of the first year, the bank is going to owe you the total deposit that you put in the first place plus the interest. Now, if you decide not to withdraw it after the first year, so after that first year, you're going to say, actually, I'm going to leave it in there, or I'm going to reinvest that deposit. What then happens is that money will stay in there for another year, and after the second year, what the bank will owe you is that initial deposit plus the interest after the first year, plus interest of that amount, or in other words, the interest of the total amount deposited after the first year, or the total reinvestment. Okay, so what this essentially means is that when you're lending or investing, simple interest is quite good because you're still going to get back more than you put in, as long as the person that you're giving it to is good for it and will actually give it back to you. But compound interest is great because the longer that time amount goes, the longer they borrow the money for, the more money you're going to accumulate, the more interest you're going to accumulate. But on the flip side, when you're borrowing money, simple interest isn't that great because you're still going to have to pay more than you initially borrowed. But compound interest can get really bad because if you can't pay what you owe after the first year, or however long your terms are, that's just going to keep accumulating, and you're just going to end up spending more and more money just paying off interest. Okay, so practical uses then. Basically, what we can do if we know the interest rate and we know the frequency of the compounds. So in the example of an annual interest rate, the interest will be calculated yearly. In a monthly interest rate, it will be calculated monthly. When we know those two things, what we can do is work out the amount owed after a specific number of compounds. Okay, so the formula for that, then, this is the maths part. The best way to do this is to do part algebra and part sort of simple figures. So I've gone for an annual interest rate, so it's going to be calculated yearly, of 10%. So simple 0.1 as a decimal. and then I'll just use P as the principal. So we don't need to know what the initial value is, and we'll just call that P. So we plug it into this table then. We'll start with the initial payment of P. So that's before any time has gone by, you're going to put in P. After the first year, you're going to be putting in after the first year, what you're going to be owed is going to be P times 1.1. And the way that's calculated is that essentially what you're going to be owed is 1 times the initial amount, so just the initial amount. And then you're going to add on the interest, or 0.1 times the initial amount, which is the same as doing P times 1 plus the interest rate as a decimal. So 1.1 times P will be the total amount owed after the first year. And then after the second year, you're just going to times that by 1.1 again, but for the same reason. And then the third year, you're going to times that by 1.1 again. Now, obviously this gets a little bit complicated as the further it goes on, but what you can do is start to see a pattern. So P times 1.1 is the same as P times 1.1 to the power of 1. P times 1.1 times 1.1 is the same as P times 1.1 to the power of 2. Just like that, third column is going to be P times 1.1 to the power of 3. And you also know, hopefully, that anything to the power of 0 is 1, which means that P times 1.1 to the power of 0 equals P. Now you can see that there's a pattern there, that for every number of years, in order to find out the amount owed, you just have to do P times 1.1 to the power of that number of years. Okay, so this does assume, though, that, as I say, this is an annual interest rate of 10%. What would be good to have is a formula that encompasses any values instead of that yearly value of 10%. And the way that we do that is just use these substitutes on the left. So we've got P is still the principal, R is the interest rate as a decimal, N is the number of compounds. So in these, as I say, for yearly, that will be number of years, but this could be monthly or quarterly or whatever. And then just W is the amount owed again. So as I say, we've got that proof from the last slide of P times 1.1 to the power of N equals W, and that's for a yearly interest rate of 10%. So what we just need to do is substitute in R as the interest rate, so P times 1 plus R to the power of N equals W. So that might look a little bit complicated, but ultimately it will just be a case of substituting in those values as and when you know them, and with a little bit of practice this should hopefully come a little bit easier. So for example, let's do a question together. So we've got Julie deposits £200 into a savings account that has a compound interest rate of 20%, which is calculated quarterly. If she leaves the money in the account for 2 years, how much money will she be able to withdraw at the end of the second year? So to do this sort of question, what you need to do first is to list all of the information that you have. So we've got the principal is 200, the interest rate is 20% or 0.2. The number of compounds is going to be 2 years times by how many times the interest is calculated in that year, which is going to be 4 because it's quarterly. So it's going to be 2 times 4 is going to be 8 compounds total. And then W is what we're trying to find out the amount owed after those 2 years. So then we just use our formula and substitute in those values. So 200 times 1 plus 0.2 to the power of 8 equals W. Same as 200 times 1.2 to the power of 8 is W. Put that all into the calculator. 200 times 4.3 will give you £859.96. That's going to be how much she's owed after the second year. So that's quite a nice way of using the formula just to find out how much money you're going to be owed after a certain number of compounds. What we can also do is work out how long it's going to take, or how many number of compounds it's going to take before you're owed a certain amount. So let's do a question that in that sense. So Terry deposits £1,000 into a savings account that has a compound interest rate of 10%, which is calculated every 6 months. if Terry is saving up to buy a car that costs £2,500, how many years will it be before he can afford to buy that car? So in the exact same way that we did the last question, we just start by listing all the information that we have. As you can see here, we do have the value that we're trying to find at the end, but we don't have the number of compounds. That's what we're trying to work out. Again, you're going to start by putting the information that you do have into the formula, and what you'll end up with when you cancel that down is 1.1 to the power of n equals 2.5. Now this is where it gets slightly more complicated, because we'll have to use a function that a lot of you might not know about. It only comes into the maths syllabus at A level, but this is the logarithm function, and what that is used to do is to work out what you need to raise something to the power of in order to get a value. So in this case, what we have to raise 1.1 to the power of in order to get 2.5. I won't go into too much detail on exactly how logarithms work, but essentially you plug it in like that, and then you can just rearrange the formula like you would any other formula, divide both sides by log 1.1, and then what you'll be left with when you put that into your calculator, if you've got a scientific calculator, then you should have a log function, will be n equals 9.61. Now this isn't quite the end of the question, because this is going to give you the number of compounds as 0.61, but what we're looking for is the number of years it's going to be, and that's actually going to be half of the number of compounds, because the interest is calculated every 6 months. So in order to find out the number of years it's going to take, we just divide that value by 2, and obviously the interest is calculated every half year, so in order to get to 4.81, you're going to have to round it up, which is going to mean that the total number of years it's going to take is 5. Okay, so that is naturally very difficult to work out in your head, but something that you can do in your head is called the rule of 72. Now this doesn't work for every value that you're trying to get to, but if you do want, this is essentially a trick for estimating how long it will take to double your money if you have a compound interest rate. And this is very simple. Basically, you take the interest rate that you've got. In this case, we'll use an annual interest rate of 10%. And you basically take that value of 72 and divide it by 10, and you're going to get the value of 7.2 years. So it really is just as simple as taking the number 72 and dividing it by the percentage of your interest rate, and that's going to get you the number of years. In this case, because it's annual, if that was a monthly interest rate, it would take 7.2 months. And below, if you did want to see the proof, we can just put that into the formula that we used before, and you can see that the number of compounds is actually going to be 7.3, which is very close to that 7.2 that you get from the rule of 72. And if you want another example, then you can use the example of 7%, and that's going to get you 10.3 years. And again, that proof will get you pretty close with the number of compounds as 10.2. So there you are. I hope that was helpful, and thank you for the request. As always, if you've got any questions or if you'd like to see a tutorial on something else, just message me or comment below. I'm still running one-to-one online tutorials for anybody that wants to learn a little bit more. Just get in touch and we'll go from there. Thanks very much.